Welcome to Operations Research. We are about to begin by the sensitivity analysis. While solving a linear programming problem for optimal solution, we assume that technology is fixed. Fixed prices, fixed levels of resources or requirements. The coefficients of variables and structural constraints are fixed. Profit contribution of the product will not vary during the planning period. The condition in the real world, however, might be different from those that are assumed by the model. It is, therefore, desirable to determine how sensitive the optimal solution is to different types of changes in the problem data and parameters. So, why we use sensitivity analysis? Sensitivity analysis allows us to determine how sensitive the optimal solution is to changes in data values. Sensitivity analysis is important to the manager, who must operate in a dynamic environment within precise estimates of the coefficients. Sensitivity analysis is used to determine how the optimal solution is affected by changes within specified ranges in the objective function coefficients, which include coefficients of basic variables and coefficients of non-basic variables. Also affected by changes in the right-hand side values. The above changes may result in one of the following three cases. Case 1. The optimal solution remains unchanged, that is, the basic variables and the error values remain essentially unchanged. Case 2. The basic variables remain the same, but their values are changed. Case 3. The basic solution changes completely. In this video, sensitivity analysis is used to answer two types of questions. The first point is, how do the changes in the available resources affect the optimal solutions? The available resources are represented by the right-hand side in the constraints. The second point is, how do the changes in the unit profit or unit cost affect the optimal solutions? The unit profit or unit cost are represented by the coefficients in the objective function. We are going to talk about what happens if we make a change in the right-hand side of the constraint. The right-hand side of the constraint denotes present level of availability of resources or requirement and minimization problems. When this is increased or decreased, it will have effect on the objective function, and it may also change the basic variable in the optimal solution. In this example, we have a company that manufactures 3 products, X, Y and Z, by using 3 resources. Each unit of product X takes 3 man-hours, 10 hours of machine capacity and 1 cubic meter of storage space. Similarly, 1 unit of product Y takes 5 man-hours and 2 machine hours on 1 cubic meter of storage space. And that of each unit of product Z is 5 man-hours, 6 machine hours and 1 cubic meter of storage space. The maximum capacity of man-hours is 900, of machine is 1400, and of storage space is 250. The profit contribution of products X, Y, and Z are $4, $5, and $6 respectively. We can formulate a linear programming problem to maximize the profit. As you see, we have three variables, x1, x2 and x3, and we have three constraints. The first constraint means the process and time of man-hours should not exceed 900 hours. The second constraint means the total processing time of machine hours should not exceed 1400 hours. The third constraint means the maximum storage in cubic meter of the products X, Y, and Z should not exceed 250 cubic meter. We can find the optimal solutions by using simplex method. Here, the following table contains results about optimal solutions. The solution obtained is x1 equals 50, x2 equals 0, x3 equals 150, s1 equals 0 hours, s2 equals 0 hours, s3 equals 50 cubic meter of the storage capacity. So, the profit becomes $1,100. Here, man-hours are completely utilized, hence, S1 equals 0 hours. Also, machine hours are completely utilized, hence, S3 equals 0 hours. But, the storage capacity is not completely utilized, still we are having a balance of 50 cubic meters of storage place, and so S3 equals 50. According to this table, the shadow price of man-hours is 9/8. It means to say that each hour increase in man-hour resource will bring in $9/8 more profit per hour. Similarly, the shadow price per unit of machine hour is $1/16, and that of storage space is 0 cubic meter. Similar reasoning can be given. That is, every hour increase in machine hour resource will increase the objective function by $1/16 per hour. Now, let us ask ourselves what the management wants to do. Question number 1. If the management want to increase the capacity of both man-hours and machine hours, which one should receive priority? The answer is man-hours, since its shadow price is greater than the shadow price of machine hours. Question number 2. If the management considers to increase man-hours by 100 hours, means from 900 hours to 1000 hours, and machine hours by 200 hours, means from 1400 hours to 1600 hours. Will the optimal solution remain unchanged? Let us consider the elements in the identity matrix and discuss the answer to the above question. By using the following table, we obtain the following new optimal solution. We have x1 equals 125/2, and x3 equals 325/2, and s3 equals 25 cubic meter. As x1 and x3 have positive values, the current optimal solution will hold well. Note that the units of x1 have been increased from $50 to $125/2, and the units of x3 have been increased from $150 to $325/2. These extra units need the third resource, the storage space. Hence, storage space has been reduced from 50 to 25 cubic meter. Shadow price indicates that resource of man-hours can be increased to increase the objective function. A solution to question number 2 above showed that, with increase of man-hours by 100 hours, and machine hours by 200 hours, the basic variables remain the same, with different values, at the optimal stage. Now, question number 3, up to what values the resource man-hours can be augmented without affecting the basic variables, and up to what value the resource man-hours can be decreased without affecting the basic variables. First, for the simplicity, let's rewrite the final table of the optimal solutions that obtained above. To answer this question, we put the table that help us to determine the range of the first resource man-hours, means the interval that tell us how much can we increase or decrease without change the basic variable in the optimal solution. This table contains in its first column the capacity that obtained above, and in its second column the coefficients of slack S1. The third column, to calculate the ratio capacity over slack S1. So, the first ratio is equal to positive 480, the second ratio is equal to negative 800 over 3, and the third ratio is equal to negative 400. The final column is to indicate the positive and the negative least ratio. Hence, in this problem, the least positive ratio corresponds to positive 480, and the least negative ratio corresponds to negative 800 over 3. Finally, to find the range of the man-hours, we subtract the capacity of the man-hours, which is equal to 900, from the least positive ratio, 480, and we add to 900 the least negative ratio, 800 over 3. Now, we are going to talk about what happens if we make a change in the coefficient of the objective function. So, let's begin by the non-basic variable. The question is, what is the range of the unit profit for product Y that will keep the optimal solution unchanged? Here, x2 is not a basic variable. Then, we can obtain its range directly from the following table that obtained above. Notice that any change in the objective coefficient of the non-basic variable will affect only its index row coefficient, and not others. From this table, we can see that the index row coefficient of x2 is equal to 23 over 4. Hence, when the present value of x2 exceeds by 23 over 4, then the present optimal solution changes, and the range of the variable x2 is the following interval. We conclude that, for non-basic variables, when its objective coefficient just exceeds its index row coefficient in the optimal solution, the present optimal solution changes. Now, let's move to the case with the basic variable. Let us ask the following question. What is the range of the unit profit for product X that will keep the optimal solution unchanged? Here, x1 is the basic variable. Then, we can obtain its range by using the following table. In this table, we have the net evaluation of Z and the net evaluation of x1. The method consists, 2 divides row of z over row of x1, and then we choose the least positive ratio, which is positive 46 over 8, and the least negative ratio, which is negative 2 over 5. We conclude that, if the present objective coefficient of variable x1 increases by more than 46 over 8, the present optimal solution changes, and if the present objective coefficient of variable x1 decreases by more than 2 over 5, the present optimal solution changes. Hence, the range for objective coefficient of variable x1 will be as follows. Okay, this how to perform sensitivity analysis for linear programming problems, and to use the results in order to make managerial decisions. Thank you for watching this video.